All right, thank you so much for staying till the very last presentation of the day. I appreciate that, and hopefully we won't go much over. This is going to be a little bit of a shift from the previous presentation, so we're going to look more at the chemistry of the systems and what's going on with reactivity testing. So everybody's talked about the R3, not going to go over this too much, but I mainly want to highlight that our goal here, our stated goal, is to determine a material's reactivity. Why would I care about that? Why does reactivity matter? Well, part of it is because we're needing to find additional SCMs, additional solutions to supplement our low supplies of Class F fly or Class F and Class C fly ash in the U.S. Since 2016, we've known that there is a shortage, with more than 80% of our states experiencing shortages. That number has only increased with further shutdowns of power plants. And so we also use fly ash for a lot of beneficial reasons in our concrete. We have some ASR mitigation, we gain some durability aspects, we densify the matrix, we can get higher strengths possibly, we can consume calcium hydroxide and bind alkalis, and we have and bind alkalis. And one solution may be to use things like ponded and reclaimed fly ashes, and we have tons of this material in the US. So 1,300 disposal sites and more than 150 million cubic yards of stored material in Ohio by itself. So I did a little back of the napkin calculation on that, and at our current consumption rate in the US, we could supply the entire United States from Ohio for the next 128 years. But that is based on an assumption that the material is reactive and is going to provide these beneficial properties that we get from our typical fly ash sources. So we need a way to identify materials that can give us the properties that we want quickly, so that we know which of these sources we can use, which are going to be beneficial to us or not. And so there's a lot of work going on in the field looking at linking reactivity measurements with performance relationships. So I'm showing here some work by Pranoy equating AMBT mortar bar expansion ASR testing to calcium hydroxide consumption in the R3 test. Also showing work by the Rylam group, including Karin, along the right side of the screen here, linking compressive strength to R3 values. And both of them have shown pretty strong relationships between those. But it still remains that we don't actually really know what's going on in these R3 tests. We're sort of guessing and hoping for the best, that we're tracking pozzolanic reactivity. And there has been some work to evaluate some of the chemical aspects and their impact on the heat generation from different pozzolans. So on the top here, I'm showing some work again by Pranoy to compare the R3 test with his modified R3 test. There's a higher sulfate and carbonate content in the R3 mixture than there is in the modified R3 test. And we do see changes in heat generation based on that change in chemistry, independent of the temperature. There's also been some work done to relate particle size to overall heat release. But besides these studies, there's not a ton known. So our objective was first to understand a little bit more about fly ashes and about fly ash reaction and the systems in which they're reacting. And then and we're going to do that through measurements of dissolution of the fly ash in alkaline solutions. And then we also want to relate that dissolution to the results and the heat release values or bound water values that we're seeing in the R3 testing. And then lastly, kind of separate from that, I also wanted to explore the idea of differences in temperature and how those affect the heat generation in our systems. So in our study, we looked at 8 Class C and 8 Class F fly ashes. We tested them using the R3 method at a varying temperature spread. We also performed dissolution studies also at multiple different temperatures and in different types of alkaline solutions, sodium hydroxide and potassium hydroxide, similar to what Farshad was showing with the pore solution extraction. And then we also assessed the percent reaction of fly ash in the R3 paste using a selective dissolution technique utilizing sodium hydroxide and EDTA. So the first thing that we can see is that this is showing heat release data at 2 different temperatures. On the top is the typical R3 method using 40 C environmental temperature, and down below is 20 C, so lower temperature, slower reaction is what we would expect to see. So the first thing is at 40 C, we're seeing reactivity in all of our materials, and that's great because these are reactive fly ashes. So we're seeing what we expect. They all exceed the heat release that we have heard is set at the minimum threshold level. But they're all kind of grouped together as well, so that makes it hard to differentiate between what's happening with any of the materials. So you can see at a lower temperature, we get a little bit slower reaction, and we see a pretty disparate behavior between the high calcium ashes and the low calcium fly ashes. Okay, so we got high calcium producing a whole lot of heat, and low calcium producing a low amount of heat, and then there's the middle of the range, about 12% calcium oxide ash right in the middle there. So we can use that to know we're going to have differences in our material, and we can look at what's happening then in a dilute dissolution system and see how there are changes in our different ion concentrations. The one thing to note here is that this is showing percent dissolution as a percent of the total bulk oxide content. So it's not showing concentrations, parts per million, those kind of values. When we analyze based on percent dissolution, what we see is that we have actually very similar dissolution from the calcium phases of the glass and from the silicon phase of the glass in the center here. So regardless of our calcium oxide content, type of fly ash, we're seeing very similar behavior across those systems. Where we see the difference in behavior is in aluminum dissolution. And so we actually see a pretty good correlation between the amount of aluminum that is dissolving from the system and the heat release that was generated in that lower temperature R3 test. I can rearrange this data a little bit now, and we're showing high calcium ashes at the top of the page and the low calcium ashes at the bottom, and I've overlaid calcium, aluminum, and silicon on each chart. And so what we see is that the high calcium ashes, we see pretty similar rates of calcium and aluminum dissolution. So that suggests that what we're dissolving is calcium aluminate glass. And then on the other side of the equation, at the bottom of the page, we see that the aluminum and silica dissolution is pretty much overlaid in our class F fly ashes. And so in that case, when we're dissolving less aluminum, we're dissolving an aluminum silicate glass, and it's occurring at a much slower rate. So I forgot to thank Tyler at the beginning, but I'm borrowing some of his data from his ASEM procedure. This is in this method, we take a SEM stub, we embed fly ash particles on it, and stick it into the scanning electron microscope, and using a VSE technique, we can assess both the particle size and the chemistry of the different glasses present in each of the fly ash particles. There are hundreds and hundreds of samples tested. Tyler has determined that there are 9 main types of glasses, and we've shown the composition of them here at the bottom of the page. So these range from glasses with high iron content, calcium aluminate glasses, and aluminum silicate glasses. So if you want to learn more about the ASEM, which is an amazing technique, I've shown the paper at the bottom here, and I invite you to check that out. But as far as our system goes, so we're showing the fast reacting glasses on the left here and the slower reacting glasses on the right. And you can see exactly which groups occurred within each of those ash sets. And so what we're seeing is that in the fast reacting glasses, we have groups 2, 3, 4, 5, and 6, which are predominantly calcium aluminate glasses. And in our slow reacting groups, we see 3, 5, 6, and 7. So if we remove the overlapping glasses, we can see that our fast reactions are occurring mainly from the glass groups 2 and 4, which is the high calcium aluminate glass and a glass with a high sodium content. And then our slow reactions are occurring in glasses that are predominantly silica and alumina based. So Karin alluded to this in her presentation, but there's a concept known as non-bridging oxygen tetrahedra. The idea here is that we're tracking the number of network disturbers, and the NBOT essentially describes the level of polymerization or the weakness in the polymerization of our glass systems. So you can see that smaller numbers represent better polymerized structures, and larger numbers are weaker kinds of structures. Maybe wondering why I'm telling you this. Well, it's because we can relate the heat release based on the number of non-bridging oxygen per tetrahedra to our dissolution. And we see a really strong relationship between the non-bridging oxygen per tetrahedra and that dissolution at very early ages. So this is the 6-hour data. And you can see the correlation coefficients for these studies over here. And what we see is a pretty big shift between 3 days and 6 days. We go from having a very close relationship with the number of network disturbers and the heat release to having essentially no relationship. We have a negative R squared down here, so showing they're not related at all. So what this is telling us is that our very early age heat release is associated with the number of network disturbers, but the long-term heat release is not. And we can see this reflected in some of our data as well. So here's our heat release, and we see pretty much a shift in the shape of the curve right around that 6 to 8 time frame. So we see very fast reaction in our class C ashes at early ages, slow reaction in our class F ashes, and then after the line, they all have really similar slope, really similar rates of heat release, suggesting that they're maybe kind of shifting to have the same sort of long-term reaction between all of the fly ash classes. All right, I'm going to skip a couple of things for time. All right, so our second question, let's go over some initial thoughts. So from this, what have you learned? Well, aluminum is the primary difference as far as dissolution from our systems goes. The silica and calcium dissolution are similar across all types of fly ash. We also saw that we have very slow dissolution in silica alumina-based glasses and faster dissolution from our class C ashes, which are driven by calcium aluminate glasses or glasses with high numbers of network disturbers. We also found out that our network disturbers govern early age reaction, but don't really have anything to do with the longer term fly ash reactions. Right, so the last thing I wanted to look at was the effect of temperature on these systems. There's a little bit of dispute about what's the best temperature to use, and I keep hearing questions from the audience about, can you just apply higher temperatures to accelerate these reactions? So we wanted to know, can we do that, and how fast can we do it? So first, we looked at the effect of increased temperature on our dissolution systems, and what we see is an increase in total dissolution based on temperature. So we have faster dissolution at higher temperature. Yay, that's what we expected, and nothing surprising there. We see very little difference as well in the amounts of total dissolution occurring in the system. They all end about between 60 and 70% total silica dissolution, regardless of the temperature. One thing that we can see from this data, though, as well, is that at 20C, we never reach, sorry about that, we never reach that threshold temperature where it kind of levels off and our dissolution slows, even out at 150 days worth of testing. So this is a very slow and continuous reaction. We do see that plateau in the 40 and 60C samples, though, pretty early on. It occurs around 14 days in the 40C sample and much quicker in the 60C sample. But when we look at actual pastes instead of dilute solutions, we see a much different behavior. So again, we talked about, you see a much different heat generation between class C and class F fly ashes at lower temperature. Those are more hidden at higher temperatures because we're getting a greater amount of reaction in the materials. And when we have a higher temperature, we do see our reactions driven much closer to perhaps final heat release value. And we see a shift in the slope of all of the heat generation curves. But one thing that you might notice is if we look at the gray sample, especially down here, and you can compare that in the 40C and the 20C sample, we actually see a pretty significant reduction in overall heat evolution. This suggests to me that for some pozzolans, we see a change in the nature of the reaction and a change in the extent of reaction that will occur in that pozzolan at higher temperatures. It doesn't happen for all of the fly ashes tested here, but we should note that some higher temperature reactivity testing may dull the amount of heat release noticed from certain pozzolans. So if you have that pozzolan, that's problematic, right? But for most of them, we should get relatively okay results at 40C. We see similar behavior when we look at the bound water results, and bound water is awesome because we can track it for a lot longer period of time. We were only able to track for 14 days in the calorimetry, but here we're going up to about a year worth of testing. We see a similar reduction in the amount of hydration product development in the system. So in the C ash on the left there, we see a pretty significant drop, about 50% of the bound water loss when we tested at 60C versus 20C. Even at similar amounts of time. So you'd think the 60C would react much more because it's reacting faster and for that similar year period. And yet we still see a much lower bound water content. We see the same kind of effect in the class F fly ash, although not as disparate at 40C. So just something to be aware of. You may see different reactions. You may be not getting the overall reactivity of your material when you test it at higher temperatures. More testing needed. So we also wanted to compare the dissolution results with the R3 paste more directly. And so here we're showing the results of those dissolution studies. We took the R3 paste, dissolved out all of the other materials, and tested the amount of remaining fly ash in solution. What we see is that at low temperatures, we have really good agreement between the amount of reaction occurring in the dissolution system and the R3 paste, but that falls apart at higher temperatures. So we see, if you look at the blue curve, they're starting to bridge apart, and the black one is even more significant. What this tells me is there's changes in the system that is the paste system that don't align with the dissolution results. So we can predict dissolution, or we can predict reactivity based on dissolution at low temperature and at early ages, but there's other things, so it's a more complicated system, right? We're also we need to think about nucleation and continued hydration, effects of diffusion of products throughout the system when we have that paste system, and that's not overall surprising. All right, so the last bit of this, we wanted to assess our ability to predict longer-term reactions using the higher temperature systems, because that's the point of the higher temperatures, right? And so here we're showing a comparison between the dissolution results at 20C across the top and 40C down the side. And what we see is that there is a pretty strong dissolution, or strong connection at both very early ages and later age. All right, so if we look at our 40C sample, so we see about 50% dissolution in 40C at about 14 days. If we find a similar amount of reaction in the 20C system, that occurs around 100 days. All right, so the finding is we can actually relate the dissolution results at longer ages, and it's a comparison of, so at 14 days at 40C, we get about the same amount of reaction as is occurring at 100 days at 20C. We have a good relationship between that. We see virtually no dependable relationship in the heat release results, but we do see some decent relationship between accelerated testing in bound water. So you can see this is kind of the same ratio of days. We had 14 days to 102 in the dissolution results. We have 7 days and 56 days in the bound water. So at least for the bound water test, it appears that we may actually be able to predict this. The problem with the heat release is that we typically don't run it for long enough, it seems. Okay, that's good. And then finally, I did also want to see how the dissolution results relate to calorimetry and bound water results. And what you can see, the green is the good stuff. I should have said that on the last slide, but we see a pretty close relationship between dissolution results and the other R3 methods at early ages, and then it turns red at later ages. So this suggests what you might have already guessed. Dissolution plays a heavy hand in reactivity at early times and early ages, and then we need to start integrating consideration for nucleation and growth processes after that. So things we've learned, aluminum is the biggest difference in our materials. We see fast reaction and fast dissolution in Class C networks because of the calcium aluminate glasses and the network disturbers like sodium. We see slow reaction in silicate aluminate glasses, and we increasing temperature, so the new stuff, it does not seem to change our dissolution behavior. It does seem to have some effect on paste-based systems. So we need to be careful about trying to accelerate our system too much, and also pay attention to the specific SCMs and whether they're actually being reduced heat because of accelerated curing conditions. And then the last one, I should have switched the order of that. So dissolution is a bad predictor of long-term reactivity behavior in our systems.